Okay, problem 10.21 is asking, a solid ball is released from rest and slides down a hillside that slopes downward at 65 degrees from the horizontal. A. What minimum value must be the coefficient of static friction between the hill and ball surfaces have for no slipping to occur? And B. Would the coefficient of friction calculated in part A be sufficient to prevent a hollow ball, such as a soccer ball, from slipping? Justify my answer. And then C. In part A, why did we use the coefficient of static friction and not the coefficient of kinetic friction? Okay, so for part A, I have that the position is at rest. So since the position is at rest, I have 1 centimeters equals 0, and this equals 0. And the solid ball, if I am finding the coefficient of static friction, I use this. And then I have angles and stuff that are given to me, like theta equals 65 degrees. And then if I use that the sum of torque will equal the coefficient for a not slipping condition, we have that this is equal to, which can be converted to A over R, which once again can be converted to, which will equal 2/5 mr squared A over R. And then we get that this equals 2/5 mass acceleration. And then if we want the static coefficient of friction, if the friction force is greater than the ball will slip, that is represented by mu n. And then we want to find the max and the minimum. So we do the sum of the x and y coordinates. F of y is 0, which is newtons minus mg cosine theta, which will equal, this is what we use. And then for the x coordinate, we use mass times acceleration, which goes to mg sine theta minus the coefficient from before, which can be converted into one of our equations that we know, where mg sine theta equals mass acceleration plus 2/5 mass acceleration. And then we have another equation that we know, sine theta, which will equal 7/5 A. Therefore, A equals 5/7 g sine theta. Okay, plugging in this equation and this equation, we cancel out 2/5 and then 5/7 g sine theta, and we eventually get that 2/7 sine theta is less than or equal to mu cosine theta, which is given by this, greater than or equal to 2/7 tangent theta, which will equal 2/7 tangent of the angle given, which is 65 degrees, which will equal 0.6127, or about 0.613, and that is part A. So for part B, we repeat part A, but consider a hollow sphere rolling down the hill instead of a solid one, so we, like a soccer ball. So we use the same as before, but for a hollow sphere, we're going to use that this is now 2/3 mr squared. And then for a not slipping condition, we're going to use 2/3 mr squared a over r. And then one of our equations given, we have F of the friction 2/3 ma. And then we do what we did before, where we find the y coordinate and the x coordinate of friction, and we plug it all into the equations given. With the same ones before for this and for this, and we eventually get that after plugging them all in and canceling stuff out, we get that 2/5 tangent 65 degrees will equal 0.8578, or about 858. And just to compare the static coefficient of friction found in part A for a solid versus the value we just found in part B for the hollow sphere, we found that the solid sphere is greater than or equal to 0.613, and then the hollow sphere is greater than or equal to 0.858. So the sphere will slip for any value of the mu that we were using, so the coefficient of range between 0.613 and this one right here, 0.858. And then for part C, we will use the coefficient of status friction. Oh, that's what we did. We just analyzed it. That was part C. Awesome.